Alright. Hey, hello guys, good evening. Today I'm gonna be going over the exam 2018. Now you guys test distributions a little bit different than ours. In our when I took the test, there were 3 midterms and a final. Now you guys have 2 tests in the final. So the distribution of topics is gonna be a little bit different. So I might not cover every single reaction that you guys gonna have on the test, just to let you guys know. Alright, so let me start with this test. So we're gonna start with nomenclature. First thing first, in the first one we see this is a Fisher projection. So the most important thing to know about Fisher configuration is that the groups that are on the sides are on wedges, and the groups that are on top are on dashes. And this rule always applies, right? It's always the same. And this is really important for you to be able to determine your R and S, right? Alright, so first thing first is I want to notice the longest chain, right? It's always like that. You always want to try to find your longest chain. So now to determine my longest chain is, I know there's a half carbon here, 1, 2, 3, 4, 5, and 6, right? Or I can count the opposite way. Now if I count this way, I'm going to have a sub on number 2. I'm going to have 2 subs on number 3, so 3, 3. I'm going to have 1 sub on number 4 and 2 subs on number 5. Now if I go the opposite way, if I start counting from this side, so let me choose purple for this. So I'm going to have 1, 2, 3, 4, 5, and then 6. So I'm going to have 2 subs on carbon number 2. So this one will win a meal, right? Because I choose the first point of difference, right? So 2, 3 versus 2, 2. So the purple wins. So I'm erasing the blue one off. I need to erase the blue stuff. So now following the purple counting. First thing first is the number of subs. I know that I have 2 methyls on carbon number 2, and I know that I have a methyl on carbon number 4, so that will be 2, 2, 4 trimethyl. And then I have 3 bromos. Alright, so it's going to be 3, carbon number 3, carbon number 4, and carbon number 5. So it's going to be 3, 4, and 5. Tribromo. And then do I have anything else for as substituents? I don't. So now the main chain, the family name is going to be a hexane. So it's going to be family, or I'll just call it root. Is going to be hexane. And then the last thing, now compared to test 1, now you have stereochemistry that you guys have to keep in mind. So stereo is when you're doing R and S for chiral carbons. So if we look at this whole molecule, we know that we have 2 chiral carbons, right? If we look at carbon number 3, right here, we see it's connect to a hydrogen, connect to this huge group up there, connect to a bromine, and connect to a CH3 3 times, right? So how your numbering is going to work for this one is number 1 is going to be the biggest group, and number 4 is going to be your lowest group, or your smallest group. And some people will confuse that to, like, if they compare BR and they compare this huge group right here, they'll be like, oh, the bigger group, group number 1, I'm going to call it. So group number 1 is much bigger than group number 2, which is the BR. And then you're just going to go and put a 1 here. But that's not how it works. How it works is you got to look at every single atom at a time. So you compare the first point of difference. So you have a carbon here, and then you have a bromine. Bromine is the biggest, is bigger than carbon. Same thing here. You have a carbon, you have a bromine, the bromine wins. You have a hydrogen, the bromine wins. So knowing that, I know that bromine is going to be my number 1. Then my number 2 is going to be either this group right here or this group. So if I look at this group right here, I know this carbon is connected to a bromine, which is connected to a CH3, which is connected to another carbon. This carbon right here is connected to 3 carbons, but we know that Br is bigger than carbon, so that will take my number 2. And then this will have my number 3, and this will be my number 4. So if I want to follow my arrows, it's going to be 1, 2, 3. So that's an R. But you gotta notice something. You never want to have your lowest group or your smallest group on a wedge. You always want to have it on a dash. So if you encounter this issue where you have your hydrogen on a wedge, what you have to do is you can just flip it from R to an S. So one of my stereo is now going to be 3S. And now looking at my second one, carbon number 4, same thing. Let me choose another color here. Let me choose green. So Br is going to be my number 1, which has the biggest, which is the biggest group that this chiral carbon is connected to. Then I'm going to look at my number 2, which I have to compare this CH to this carbon to this CH3. Now, if I look at this carbon, the carbon right here, and this carbon right here, because I know that CH3 is smaller than both, right? It's immediately, right? Because this carbon is connected to 3 hydrogen, while this carbon is connected to a hydrogen, Br, and a carbon. This carbon right here is connected to a Br, and this carbon is connected to 3 carbons. So now if I compare these 2 carbons, the one on the top and the one on the bottom, I see that the one on the bottom is connected to a Br, which is the same thing for this one. This one is connected to a Br2. It's connected to a hydrogen. This one is also connected to a hydrogen. But now from the bottom side, I have it connected to a C, which is connected to a CH3 3 times, while this one is connected to just a CH3. So that will tell me that the one on the bottom is bigger than the one on the top. So that will take number 2. That will be my number 3, and that will be my number 4. So if I want to do the R and S, this is an S. But don't forget, my smallest group is on a wedge, so that will cause it to become an R. So let's now put the whole name together. So my other stereo is going to be 4R. So putting the whole thing together, you always want to start by putting the stereo at the beginning, right? So 3S, 4R. And now you gotta put the substituents in the family name. So you have tribromo or trimethyl, and remember the T doesn't play a role in alphabetical order, right? The only thing that counts is the B or the M, right? And B is alphabetically higher priority than the M, so it's gonna go first. So 3, 4, 5. Tribromo. 2, 2, 4. 2, 2, 4, trimethyl, and then you have at the end hexane. Alright, so that's pretty much it. Now let's move on to the other one. This one, there's a new group that you notice here is that we now have alkenes. So a couple things to know about alkenes, and the most important thing to know about alkenes is that they can have stereochemistry, and that stereochemistry can be Z or E. Z meaning they are on the same side, so it's a quick way to remember it. And then what I mean by the same side is that the big groups are on the same side. And once we're doing this example, I'll show you what I mean. So the first step is also the same thing. You gotta try to find your longest chain possible. So if we start counting from, let's pretend we can start counting from here. 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8. So it's the same, either I go both way, right? But now I gotta see which way I should count, right? If I count this way, I'm gonna have an alkene. So the alkene will count as a, when you're doing the number, it's gonna count as a group. So you're gonna count it as like a sub. So you're gonna have 1 on number 3, 1 on number 4, 1 on number 5, and 1 on number 7. Now if I go the other way around using my purple, 2, 3, 4, 5, 6, 7, 8. So now I have a group on number 1. Immediately the purple wins, so I can erase the 1. Because remember, you're looking at the first point of difference, right? So let's start with subs. So we have two subs here. We have this group right here, and we have this huge group here. So we know that on carbon number 5 we have a methyl, and on carbon number 4 this is a little bit more complex type of sub. But to do this is I just take this one and name it separately. So I know this is a 3 carbon chain, so it's a propane, right? But it has a double bond, and it's a substitution, so it has to end with L. So this would, and remember, when you're doing subs, you always want to start counting from this side, right? 1, 2, 3. You always start counting from the side of the main chain. So if I want to know the name of this sub, it's gonna be 4 prop. I like to put the number inside, so it'll be like 2 enol. This is how I like to do it. You can also write it as or 2 prop enol, like that. The reason why I like doing it this way is because later on you're gonna like have much more substitutions, and you're gonna have so many numbers. It's gonna get a little bit confusing when you're putting it outside like that. So you're gonna see me most of the time sticking with this nomenclature. Just a heads up. Alright, so do we have any other subs? It doesn't seem like it. So now let's look at the family, the root. So I know it's an 8 carbon, right? So that's a octa. It's usually octane, right? But we have double bonds here, and if you notice, we have 2 double bonds. So that's a diene. So how would write this? It's gonna be octa, and then it's gonna be a 1, 5 diene. You can also write that as a 1, 5 octadiene. Alright, I'm gonna erase this one because it's just there's so much. Now, here I want to mention something really important that I think Dr. B, she's gonna like trick you in the multiple choice, and that's this A, right? She might give you an A that looks like this: oct 1, 5 diene, with no A here. So you gotta be careful. Like, this is such a small thing that you can overlook, but there has to be an A here, unless it's just a 1 alkene group. If it's a 1 alkene group, then you can just have octene, right? You don't have to have the A here. Just keep that in mind. You always want to have an A here. Now, the last part of this is going to be stereo. And this stereo is a little bit different than R and S because we're talking here about double bonds. And when we're talking about double bonds, as I mentioned earlier, you have to consider Z and E. And what I meant by having groups on the same side, I'm going to mention right here. So how I like to do this type of stereo around the double bond is I usually highlight the double bond, and then I look at the groups around it. So I have this group right here. I have a hydrogen on this side. Let me just use a different color here. I have a hydrogen on this side. I have a carbon here, and I have this huge chain on the bottom, right? So now, what I do is I compare on each side of this alkene which one is bigger, and then next to the group that's bigger I put a H representing high or high priority, right? So if I compare this thing to the hydrogen, I know that the ethyl is going to be bigger, so I put an H on the bottom. And then I know that this huge group, this group right here, is bigger than just a CH3, right? So that will be my H. And then those two groups on the top will be my low, right? So as you can see, I have the two H's on the same side. They're both on the same side, right? They're both on the bottom. So that will tell me that the stereo is Z. Now another thing that I would like to mention here is when you see those double bonds at the end, probably some of you thought right now, why did I not do stereo for these? The reason why I did not do stereo for these is because at the end of those double bonds, I have two hydrogens, and those two hydrogens, I cannot compare them, right? There is no comparison, so that's why. So they're both small groups, right? There has to be different. If they're not different, there is no stereochemistry around double bonds. So just keep that in mind, because that's can also be tricky sometimes. So now let's put the whole name together. So it's gonna start with a Z, and we have 5-methyl or 4-prop 2-propenyl. So we know that M comes before P, so that will be 5-methyl 4 prop 2-enol, and then it's gonna be 1 5. Actually, let me just put it the other way. Octa 1,5-diene. Alright, and also another thing that I would like to mention is you only put dashes. I know this is like I mentioned it last time, but you always put dashes only when you have it's between letters and numbers. So you see here, I didn't put any dashes there because they're both letters. The only time you put a dash in between them is when you have a letter and a number. Alright, so now moving on. We have a cyclohexene, right? So that's my root. So my root is going to be a cyclohexene. So if you notice here, I didn't put 1. And I don't remember, but I think she now starts the moving point if you put 1. I'm not sure. Don't quote me on that. Because it's obvious that the alkene is going to be on carbon number 1, right? That's why you don't want to put 1 on when the alkene is on carbon number 1. So if I want to start numbering, I have 1, 2, 3. And obviously, I'm not going to start counting from the other side around. I'm not going to start 1, 2, 3 like that, right? Because I'm going to have higher number of substitutions, and I don't want that. That's the first thing that you want to do. Now, let's look at subs. So we know on carbon number 1, we have an ethyl. On carbon number 3, we have a bromo. Well, actually, we have another ethyl here, so it should be 1,3-diethyl. Alright, those are my two subs. Now let's look at stereo here. We can see carbon number 3 is a chiral carbon. The reason to why is that is because it's connected to 4 different groups: a bromine, an ethyl, a carbon connected to a carbon with a double bond, which means it's like it's connected to 2 carbons, right? And then it's connected to a carbon from this side. So let's start with numbering here. So I know that Br is going to be my biggest group, so it's going to take my number 1. Now the second thing is I'm going to compare these two. I know this carbon is gonna win because when you have a double bond, it's like, so if you have a carbon, double bond carbon, this carbon is like it's connected to 2 carbons, right? This is how you always want to count it. Right? Just keep that in mind. That's why this one will have a bigger molecular, bigger size, so higher priority. And then this will be my number 3, and the ethyl will be my number 4. So that will be going counterclockwise, so that's in S. Right? And now I gotta check 4. My lowest priority was a dash, so I'm good. So it stays in S. So now it's gonna be 4S. Well, you don't have to put 4S, you can just put S because there's only one stereo center, right? So you don't have to mention the 4S. Now the other thing is this double bond right here. Why this double bond, you don't have to put a Z or E for this one. The reason to why is that is if you have any cyclic rings, right, or cyclic compounds, you don't have to mention Z and E unless it's bigger than 8 carbons. The reason to why is that is because anything that's smaller than 8 carbons, it's assumed that it has to be in a cis format. Again, the reason for why is that is because, remember, she discussed that in class, and she says that cyclic below than 8 are more stable in cis configuration. So that's why you don't have to put Z. And when I say cis, I mean Z, right? Z and cis are the same. Right, but we use Z in nomenclature. Just keep that in mind. So now let's put the whole thing together. So as always, you start by the stereo first. So S. Then you gotta put your substituents. You have either bromo or ethyl. B comes before, alphabetically before the E, so it's gonna be 3 bromo. 1,3 diethyl. And then you have a cyclohexene. So cyclohexene. Alright, everything's pretty straightforward. So moving on to the facts section, and the biggest part of this test is going to be having SN1 and SN2, right? This is the big part. And couple things that you guys have to, actually, should I mention them now? Yeah, actually, let me mention a couple things about SN1 and SN2 here. So you guys always have to know that SN2, some people confuse that as a 2-step reaction, but it's not. The SN2 represents that it's a second order reaction. Second order reaction. And when we mention second order reaction, what we mean is that the rate of the reaction depends on 2 things. And those 2 things are going to be the nucleophile and the reactant. Right? The second thing that you should keep in mind always in SN2 is that SN2 is a 1-step process. 1-step process. And the last thing is SN2 is favored to be primary, better than secondary, much better than tertiary. Tertiary, like, I don't want to say never because this is chemistry, so I would say almost never happens, right? Now, when we're talking about SN1, it's a first order reaction. And what that means is that the rate of the reaction depends only on the reactant. Now, this one is a 2-step process. 2-step process. And then the last thing is tertiary. For this one, tertiary is better than secondary and better than much better than primary. Right. And the other thing to notice is during SN1, there is a formation of a carbon cation. And that's why tertiary is better in SN1 compared to SN2. The reason to why is, remember, the stability of a carbon cation is tertiary better than secondary, better than primary. Now, when we're talking about SN2, the reason why it's primary better than secondary better than tertiary is because the whole reaction happens in 1 step. So the nucleophile has to attack the carbon that's connected to the leaving group, and the leaving has to leave. Another thing that I forgot to mention about SN2 and SN1 is that SN2 is always 100% inversion, while SN1 is going to be 50% inversion and 50% retention. Again, see, the carbon cation plays such a major role in SN1 for all of this to happen, right? In one of the steps, let's pretend we had, right, and the BR is connected right here. Right, the first step, this BR is just gonna leave, and you're gonna end up with this partially positive. Because now you have this partial positive, the other group that we're attacking with, let's just call it B, okay, base, it can either attack from this side or this side. Now when we're doing SN2, yeah, let's pretend we have something like that. And let's pretend we have Na iodide here. So what's gonna happen is this iodine can only come and attack from the top and kick off the Br. It cannot come from the bottom because the Br is big and it's gonna create too much steric hindrance for it to come attack from the bottom, and that's why there's 100% inversion in SN2. So this is a big no-no, and the Br is gonna leave here. So this is the major rules about SN1 and SN2. Just keep that in mind. Later on, once I start the action, I'm gonna talk about how you can separate between SN1, SN2, E1, E2. I have a whole flowchart that makes it so much easier than like trying to memorize it. Alright. So now let's jump into the first questions of facts. Consider the reaction below in the box. Draw the transition state for the rate determining step. Alright, so the first thing that you want to notice here is that you gotta determine if this is gonna be an SN1, E1, SN2, or E2. So the first thing you notice is that this is a weak base. This is a weak base. It's a secondary, and you notice at the end that there's a double bond. So you know that this has to be in E1. I don't want to mention how you exactly find the differences between them because I'm keeping this section for just before the reaction. But just remember, when you have a weak base and a secondary bromine, it's just gonna form a E1. And remember, in E1 SN1 have the same mechanism. It's a two-step process, and the first step is gonna be the leaving group leaves. And another thing that I forgot to mention earlier is that the rate determining step is the step where the bromine or any leaving group just leaves. And that's really important. Is the reason why this is important, because this is the thing that determines the order of the reaction. So my nucleophile cannot attack until this Br leaves. So the leaving of the Br is the step that determines how fast the reaction is gonna go, and that's why it's called the rate determining step. So she's asking to draw the transition state for the rate determining step. So this one should be pretty straightforward, is that the Br is just gonna leave, right? And remember, when the Br leaves, it's gonna take those electrons and then it's gonna leave this carbon positively charged. So if I want to draw the transition state, this bromine is partially negatively charged and this carbon is partially positively charged. Alright, so now the second question is, place the following carbon anion in order of increasing stability. 1 is going to be the least stable and 3 is going to be the most stable. Now, I mentioned before that for carbon cation, the stability is going to be tertiary is better than secondary, which is better than primary. Now for carbon anion, it's the opposite, which is primary better than secondary, better than tertiary. I should also mention the radicals that we'll encounter later on. That actually we encountered it before when we did for the test one, but I'm going to mention them again here. So for radicals is like carbon cation, the stability is going to be tertiary better than secondary, which is better than primary. Now let's compare all three of these. So first thing you notice is that these two are both secondary carbon anion. Alright. Oh no, I don't know what to do here. That's hard. So let me just skip those. Alright. Let's look at this one right here. This is a tertiary carbon anion. If I look at my rules, I see that tertiary carbon anion is the least stable. So that immediately tells me that this has to be my one. Now comparing these first two, if you notice, everything is the same except of having this chlorine on there. Right? This chlorine is the major difference between all of them. And remember when we talked before about induction, right? This is gonna pull electron by induction. And why is that a good thing? Is because it's gonna allow the delocalization of the charge, right? If you have a delocalization of the charge, that's a good thing because you don't want to have a condensed negative charge cloud. So that tells me that this is why the carbon anion with the chlorine is going to be the most stable, and this will be my second most stable. So now place the following alkenes in order of increasing stability from the least stable to the most stable. Before we start on this one, I would like to mention two things to know about this one. So the first thing is that when you're talking about stability of alkene, the more subbed or the more substituted the alkene is, the more stable it is. More stable. The second thing is when you have those bridge cyclic compounds, is you always you never want to have a double bond on. Hey, let me just draw one. So those carbons here, let me just highlight these. Those bonds, that's two, and can you guys not see that? Those right here, and these also. You never want to have a double bond right here, unless there is a ring that's formed by those bridged carbons that is 8 carbons. So if you have anything less than an 8 carbon cyclic, you cannot form this double bond right here. This is not stable at all. So if I look at this example, the first one right here, right, I have a double bond next to the bridge, adjacent to the bridge. This is my bridge, right? And I have a double bond right here. Now, the first thing I know that this is automatically not stable unless there's 8 carbons. There's an 8 carbon ring. So if I count the number of rings, I have to start from here. 1, 2, 3, 4, 5. So that's a 5 carbon ring. So another thing to mention here, the ring doesn't have to be only this way. I can form a ring any other way, right? So I can count also 1, 2, 3, 4, 5, 6. That's still a 6 carbon ring. That's still not good. I want 8 carbon ring for it to work. So that automatically super unstable. Super unstable. Unstable. And that will take number 1. So now, looking at the other two, we notice that there is no double bond adjacent to a bridge. So this is good, right? Because if it was adjacent to a ring, that won't be stable because you will need 8 carbons, right? So how you compare these is by the number of substitutions that connect to the alkene. So if I look at all these, the way how I'd like to do it is that by start highlighting the double bonds, right? And then I look to what is connected to those double bonds. So I count the number of carbons that's connected to those double bonds. So I have 1, 2, 3. So there are 3 carbons. You can also call it as a tri-substituted. This double bond here is connected to 2 carbons. So that's a 2 carbons. So that's a disub. So as I mentioned before, the more sub the alkene, the more stable it is. So I know that this will be my most stable, and this will be my second most stable. That's pretty much it for alkenes. So just remember that for alkenes, the more sub the alkene is, the more stable it is. And then if you have a less than 8 carbon and a double bond adjacent to a bridge, that's not stable at all. Those are the only 2 rules, right? So now label each of the compounds below as chiral or achiral. So there's lots of confusion that happens here about carbon being chiral or the compound being chiral. When you're talking about a compound being chiral or achiral, so when a compound is achiral, it means it's symmetric. There's a plane of symmetry. Plane of symmetry. Now when a compound is chiral, there is not a plane of symmetry. Not a plane of symmetry. Symmetry. Now when a carbon is chiral, it means it's connected to 4 different groups. When a carbon is achiral, it means it's not connected to 4 different groups. So to compare these two, let's first look at the first one. We want to try to find a plane of symmetry in this compound. Right? If I try to split it down the middle, right here, I see that if I want to fold this together, I know the hydrogen and the hydrogen align, the bromine and the bromine align, and the aldehydes. Also, another thing that I would like to mention here is when she writes CHO like that, that's not alcohol. This is aldehyde. This is C double bond O hydrogen. This is This is an aldehyde. So that will matter a lot, especially when you're doing like you're counting the highest priority, but not for now. The alcohol is COH. So COH is alcohol. I just wanted to mention that really quick here. So now, once I fold them, I can see that the bromine and the bromine align, the hydrogen align, and the aldehydes also align, right? So that tells me that there is a plane of symmetry and that this molecule is achiral. Achiral. I know it might sound, it doesn't make any sense when I say achiral being symmetric because it's an A, like something that is not. But how I remember it is achiral is there is a plane of symmetry. So now when we look at the second one, this type of question brings up a lot of issues because it's kind of hard to see the plane of symmetry. But there, just like you know, there is a plane of symmetry, and to be able to see this plane of symmetry, you gotta consider this single bond right here plays a major role to why there is a plane of symmetry, right? Because there's this single bond right here, it allows those two groups to freely rotate, right? They can rotate back and forth, right? So how this is gonna how the easiest way for you guys to see it is, let's pretend you have a vertical plane, and the other plane is gonna be flat like that, right? And the first one is there's the ring right here. What's gonna be like that? There's an iodine right here. There's an iodine right here. And those two planes are connected. Now the other one is laid flat, so that would look something like that. The BR, the iodine right here. So now if I want to split this plane of symmetry, it's just gonna go through those. So the I and the BR, there's no plane of symmetry between the BR and I, right? If I split it right here, those two don't align. So someone will be like, oh, there's no plane of symmetry, right? This is where the confusion happens. But once I split it in the middle like that, the BR and I, they're not gonna fold each other because they're in the middle of this cut that I'm making. So the only two that are going on top of each other, so this fold right here, is where the plane of symmetry happens. And this is where the confusion happens usually, is that what people usually do is they just split in the middle and be like, oh, the BR and the I don't align, so there is no plane of symmetry, so that's chiral. But as I'm saying right here, if you can see that, once I turn this benzene ring flat, the BR and I are aligned, and once I cut through them, I'm not gonna even see them because the plane of symmetry is just gonna cut through them. So that tells me it's gonna be achiral. Alright, so now moving on to number 5. In the box provided, place the letters. Alright, so moving on. Before we start this one, I would like to mention a couple of things about how to determine the strength of a nucleophile and the strength of a basic. You're not gonna use the basicity one that much, but it helps later on. So if I look at the periodic table, let me just add a page here. Alright, so if okay. So if I'm looking at a periodic table, so let's pretend it looks like that. So when I'm looking at the trends across the table, we mentioned before that electronegativity increases to the right and up the periodic table, right? So that's for electronegativity. Now when it comes to nucleophilicity increases as we go down. So as we go down, the trends are the size increases, the size of the atoms, and then the basicity decreases. The basicity decreases, And then nucleophilicity, so I'm just gonna NUC here, increases. And then when I'm moving right and left side, so as I mentioned, electronegativity increases when I move to the right. Now for nucleophilicity, it's the opposite. So nucleophilicity increases when I go to the left, increases, and then basicity increases also this way. Basicity increases. I know there's a lot to remember and that can be overwhelming, but trust me, with time, all of that just gonna become natural to you guys. So when I'm looking at these two reactions here, the first thing that you wanna do is read the question. In the box provided, place the letter of the reaction with the faster rate if the rate is the same, right? S in the same box. So if I look at those two, I know that for both of them, I have the same reactant, I have the same product, and I have the same both product. And the only difference I have is this reagent right here. Now, the first thing that I notice is that this is a primary, right? And I'm having substitution, so I know automatically that this is going to be an SN2 reaction. And do you remember when I mentioned before SN2 reaction is a second order reaction? That means it depends on two things. The nucleophile, the rate of the reaction depends on two things. The nucleophile and the reactant. So knowing that, what you want to do first is look at the reactant. For both of the reactant, we have the same reactant. So that doesn't help me to figure out which one is faster. Now if I look at the nucleophile, I notice this one has it's S and this one has a P. So if I look at the periodic table, I notice that the phosphorus and then the S comes in this order, right? There's, do I have a periodic table at the end of this? No, I don't. Alright, so I have phosphorus and sulfur, right? So those two are in this way next to each other. And as I mentioned before, nucleophilicity increases as I go to the left. And the stronger the nucleophile, the faster the reaction is going to go. So I know that my phosphorus is going to be stronger than my sulfur. Knowing that, I know that this will be my stronger one, so that will be my faster one. And that's why it's B. Another thing that I would mention here is if you notice that the reaction is an SN1, the answer is always going to be, well, not always, because she might give you two different reactants, so I wouldn't say always. So if you have an SN1 and you have the same nucleophile, it's always the same. But if you have an SN1, two different reactions with different reagent, you gotta determine which one's gonna be faster based on the reactant. So if the reactant is a tertiary compared to a primary, the tertiary SN1 is gonna be faster than the primary SN1, as I mentioned before. Alright, so number 6, label each of the following pairs as identical: structural isomers, conformational isomers, enantiomers, or diastereomers. So let me mention a couple things about this one. So identical is just going to be the same, right? Structural isomers is the same formula, different connectivity. And then you have enantiomers. How I like to think about it is it changes completely from an R to an S. Diastereomers, one of them change and the other one stays the same. So for you to have diastereomers, you have to have at least 2 chiral carbons for it to work. Chiral carbons. And what happens in chiral carbons, you'll have one carbon that's R and stays R, and the other carbon is R and becomes S. So one of them changes, and that's why it's a diastereomer. I don't think there's a diastereomer example here. No, I would like to have one. Maybe I'll pull up one and then add it to here. So let's compare these two. First thing is you're comparing these two. This is a Fisher configuration, so that means that this is a wedge here. This is a wedge here. And hydrogen and CH3 on dashes. So first thing first is you gotta number them based on priority. So we know that hydrogen is the smallest, so we'll take number 4. Bromine is gonna be my biggest, so it's gonna be my number 1. Then I have NH2 compared to my CH3. NH2 will, oh well, I forgot to erase that, but NH2 is a little bit bigger than the CH3. Well, I'm comparing the nitrogen versus the carbon, right? So nitrogen is a little bit bigger than CH3, so I'll take my number 2. And then carbon is going to be the smaller. So if I want to do the circle around that, I'm gonna have 1, 2, 3. So that's a S. But you notice how I have a wedge on the on group number 4. That will cause me to flip that, and it becomes an R. Right. Now let's look at the other one. So I know this is gonna be my number 1. Let's just use a different color here. My number 1, my number 4, my number 3, right, the CH3, and then my number 2 is gonna be my NH2. So if I do the circle around it, so this is clockwise, and you see here I have my atom number 4, which is the hydrogen, on a dash, so I'm good. I don't need to flip anything. So that's an R. So they're both, they have the same conformation. This means those two are identical. Identical. If one of them were to be like R and the other one is like S, let's pretend here, then there would be enantiomers. Just keep that in mind, because enantiomers are just mirror images, and those two are not mirror images. They're just the exact same, but they just have different different orientation of the BRs, but end up being the same exact molecule. Now let's look at the second one right here. So if you split that down like that, you notice that there's mirror imaging, but I'm not sure yet. So what I would like to do here is I would like to do RNS, which is the easiest way to determine if something is identical or not. But if you notice something here specific, is that there's a plane of symmetry. So if you have a plane of symmetry and mirror images, usually they're identical. But to be sure, let's just do RNS, because RNS is the easiest way to determine if something is identical or not. So this is going to be on the wedge, right? This is going to be on the wedge. Dash and then dash. So immediately I know that my hydrogen is going to be my number 4. Then bromine is going to be my number 1, 2 right here, because this one is connected to a carbon, which is connected to a carbon, which is connected to a BR. This one's connected to 3 hydrogens, so that will be my number 3. So now if I'm going to go around, 1, 2, 3. So that would be an S, but my hydrogen is on a wedge, so that will become an R. Now let's look at the bottom one. Same thing. I know my BR is going to be number 1. I know my hydrogen is going to be number 4. This will be my number 2, and this will be my number 3. So 1, 2, 3. This is an R, but again, I have my hydrogen is on a wedge, because this is the Fisher configuration. So that will switch it to a, this is an R, becomes an S, yep. So this one becomes an S. So those are my 2 confirmation. And you notice something when when I'm like writing it down, I always put like S and then arrow R, because what happens sometimes, people if some people just write R, they come back and like look at it quickly when they're reviewing their test, and they become, oh, this is S, and they just fix it to an S, and then they will forget that you have to flip this one. That's why I like to write S and then R. Now let's look at this other side. I know that BR is also number 1, hydrogen is number 4, this is going to be my number 3, and this is going to be number 2. If you notice, it's the same numbering of groups, right? If you remember them, it's just different orders, right? So it's just going to be 1, 2, 3, 4. So this is a S, but remember, hydrogen is on number 4. It's going to become an R. Now if I look at the bottom part, BR is 1, 4, 3, and then 2. So 1, 2, 3. This is an R, but then it becomes an S, because again, hydrogen is on number 4. So R, and then becomes an S. And you notice that all 4 groups, they have the same configuration. And that tells me that they are identical. Now, moving on to the last part, C. So first thing first you notice is that there is something majorly different here, right? The difference is that you see how this carbon right here is connected to an OH and the hydrogen, while this carbon right here is connected to CH3 and OH. Now we have to notice is this is the same, wait, is one of the question asking identical? Yeah. So she might add also like different compound where like one of them will be like completely different, but she doesn't have it in this option. So if I look here, I notice that there's a CH3 missing, but if I look down, it's connected here. So there is different connectivity. You see these two, there is a different connectivity. So those two have the same chemical formula, but they have different connectivity, meaning that these two are structural isomers. Structural isomers. Alright, so now moving on, in the compound below, will rapidly undergo E2, place Y for yes in the box. If the compound will not, place N for no in the box. So here the major keyword in this question is rapidly. When she says rapidly, this means that there is a stability, right? We're not talking about something that's just gonna form in E2. Like there's lots of molecules that can form just in E2, right? But it can be slow. If it's slow, this means it's not stable. So looking at this one here, do you remember when we have cyclic hexanes and we want to form an E2, you always want to have a trans diaxial. And what I mean by that is that the leaving group and the hydrogen, they both have to be on an axial position. They have to be on an axial position. So now looking at this group right here, how I like to do it is, because she wants it to be rapidly, I want to have this third butyl right here, I want to have this group on an equatorial, right? Instead of me drawing out this chair conformation, there's a quicker way that I've went over in my workshop. What you do is you draw all the wedges across, so you get this is my leaving group, right? So I want this leaving group to be axial, right? So if I look here, I will see that when you're moving from wedge to wedge across a cyclohexane, you see this one is equatorial. Now the next one has to be axial, right? And then the next guy has to be equatorial. It's like alternating. And then the next hydrogen on the wedge right here is going to be axial. And the next hydrogen here on the wedge is going to be equatorial. So that's a quicker way than just drawing the chair conformation and trying to figure it out. But because my more stable chair conformation is going to have the chlorine on equatorial, that's not good. That's not stable. And thus E2, you got to notice here that E2 will form, but it will be much slower and not stable because I'm going to be using the least stable chair conformation. But it will happen, but not rapidly. So that will let me get to an end. Let me just explain by drawing the chair conformation, because I know some people cannot just solve it without the chair conformation. So let me just draw it really quick here. So looking at this, first of all, I want this third butyl to be on an equatorial, right? This is my equatorial right here. This is my hydrogen. So I know 1, 2, 3, right? So 1, this is my carbon number 1, this is my carbon number 2, and this is my carbon number 3. Remember when we talked about it in test 1, wedge is always, for reference, for me, I work with it as wedge being up and dash being down. So if it's wedge, it's going to be up. So on the third carbon, this has to be pointing up, which is a chlorine, and then the hydrogen will be on axial. But that's not good because I said the chlorine has to be on axial for it to have a rapid E2. So that's not good. So no reaction will happen rapidly. Now looking at this one right here is same thing, but if we look here, we know that we have a bridgehead. Right? And remember when I mentioned something really important about bridgehead is that if you want to have a bridgehead and a double bond, you want to avoid having the double bond on these right here, right? Unless there's 8 carbon or more. 8 carbon or more. So if I form, let's pretend I formed the double bond right here, right? And I want to count to find 8 carbon ring. So I have 1, 2, 3, 4, 5, 6. That's not good. Now, maybe there's another way I can count for a ring. So there's 1, 2, 3, 4, 5. So both of those rings that I tried to count add up to less than 8 carbons. So having a double bond right here is not stable. That's actually super not stable. So that will tell me that an E2 rapid reaction won't occur. So that's why I have to put an N for both of them. Alright, so before we jump into the reaction, I would like to go over a couple rules. So how I want to think about this is I kind of have like a flowchart that makes it easier for me to recognize like which reaction is which. So the most important thing is that I start by looking at the nucleophile. Now there are two types of nucleophile. There is a strong nucleophile. So strong. And that's usually indicated with like a charge on it. So like charged, I would say. And there's like a weak nucleophile. And that usually is like neutral, right? It doesn't have a charge. Neutral. Now let's start with the strong side because I think this is the like easier way. So if I have a strong charged nucleophile and it looks bulky, so it's something like turbutyl, turbutoxide, TEA, triethylamine, DMP or LDA, DMP or LDA. Those are all strong, bulky bases. What's gonna happen? I'm gonna have E2, and I'm gonna have the Hoffman product. The Hoffman product is also known as the least sub. Then we'll go over more examples when we start doing reactions. Now the second part is the non-bulky ones. And then when you're not talking about the non-bulky ones, you have three versions. You have primary, you have secondary, and you have tertiary. So primary is you're gonna always have SN2, no questions asked. So it's gonna be SN2 and it will be a full inversion, right? Full inversion. Now when you have a secondary, you have two options. This is a confusing one where everyone gets confused with it, right? The secondary, you have either can be a strong base, that would include like stuff like RO minus, NH2 minus, OH minus, strong but not bulky bases. And that will end up with also an E2, but this time it's Zaitsev. And that what means is it's going to be the most substituted alkene. Now the other part of secondary is having not a strong base. If you don't have a strong base, that would end up with an SN2. Now the tertiary part, well, it's tertiary. Even if you're using a strong nucleophile, you're still going to end up with a SN1. Right? Well, it's going to be, remember, SN1, E1 come together, so I should just say here, SN1 and E1. So remember, tertiary is going to be always SN1, and primary is always SN2. But when it comes to secondary, you have to decide if it's an SN2 or an E2. Now when it comes to weak, so anything that's weak, you're always going to have a mixture of SN1 / E1. And remember when we're talking about SN1, there is always a retention and inversion. Retention and inversion. Inversion. If you keep that in mind while doing tests, you're never gonna miss a reaction. because this like lays out everything, right? So let's jump into the reactions here. So first thing first is I look at the Br. It's a tertiary, right? This is a weak, right? So what does that immediately tell us? It's going to be SN1, E1, right? Also, guys, another thing to mention that I have to mention here is heat. It's important to have heat in an SN1, E1 reaction because when you have an SN1, E1 reaction, the major product is always going to be the SN1 part. Now, the minor product is going to be E1. Once she puts heat in the reaction, that will gives us more concentration of E1, but that doesn't make the E1 more major, right? Or the major product. So remember in SN1, the first reaction is what's gonna happen is the leaving group leaves SN1 E1. So this guy's just gonna leave, and then you're gonna end up with a positive charge here. Positive charge on a tertiary. That's great. That's super stable. The only thing that's more stable on this is having an allylic carbon cation. So that's super stable. Now, remember, there's an SN1 and there's an E1. Now, when we're talking about SN1 here, is we're not going to consider inversion and retention because there's no stereochemistry around this carbon right here. So, the product what's going to happen is the substitution part is going to be my major one, as I mentioned. So I'm going to have 1, 2, 3, and I'm going to have more of that, and I'm going to have O, CH2, CH3, and then my minor is going to be E1. But you notice here, there is 2 boxes for E1. The reason as to why is because you have 2 adjacent hydrogens, right? You have a hydrogen right here. You have a hydrogen right here, and you have a hydrogen right here. Now this hydrogen, there isn't a hydrogen here, right? But those 2 hydrogens, okay. This hydrogen and this hydrogen are the same, so I'm not going to consider this one as a different hydrogen. Right, there are 2 different hydrogens, so what's going to happen is I'm going to have a double bond either here, that's going to form. A double bond's going to form here, or the double bond's going to form here. So let me draw the product of this one. So I'm going to end up with a cyclohexane with either a double bond right here or a double bond right here. Right, and then, well, if I were to compare between those 2 products of E1, which one's going to be the more stable one? Remember, alkene, the more substituted the alkene is, the more stable this one. So this one would be the more stable out of the 2 alkenes, this one. Right, so now, moving on, NBS and light. This is not neither a substitution or a elimination reaction. So NBS is going to form a radical on an allylic carbon. Now, allylic carbon is a carbon that's adjacent to a double bond. So this carbon right here is called an allylic carbon. A carbon that's right here is called a vinylic carbon. Just keep those 2 terms in mind, because it's a multiple choice, so she might ask you as like a concept question. So just keep that in mind. So the first step of NBS is gonna form a radical on a allylic carbon. So the only allylic carbon that I can see is, well, there are 2 allylic carbons, right? There's this carbon right here and there's this carbon right here. But this carbon is fully saturated. It has 4 bonds, right? It's not going to have a radical. It's not going to lose a hydrogen any way possible because it doesn't have any hydrogens connected to the carbon. So I'm going to form a radical right here, right? But this radical can resonate, and that's why you have 3 boxes here, 3 or 4, 3 boxes. Right? You have 3 boxes. This means you have different products, and the reason to why you have different products is because you have this resonance. So the first resonance, this radical can form a double bond with one of the radicals right here, and then kick off one of the radicals up here, and then you're gonna end up with a radical right here, and then a double bond here and double bond here. Now the other radical, the other resonance contributor is gonna be this radical is gonna resonate this side with this point, and it's gonna go here, and then you're gonna end up with This double bond here, and now the new double bond is going to be formed right here, and then you have a radical at the end. So now I have 3 products. So wherever I have a radical is going to be replaced with a Br now. So if I were to draw all of that, the first one's going to be right here with a Br. The second one is going to be right here with a Br. And the last one, this actually, usually guys remember this reaction really well, because this reaction, you're going to use it a lot in synthesis, especially now at the beginning. And then it's going to go up here. And then the 2 BRs are going to, the BR is going to be right here. So those are all the 3 products that I got based on resonance. Now let's look at this one here. So first thing first is, I gotta look. I have 2 leaving groups. I have a Br here and I have chlorine here. Well, how am I gonna choose which one? Remember, something really important is no SN2 on sp2. So this one Br cannot, this one cannot have any SN2, SN1, even like SN1 you're not gonna have it because you don't have that MTP orbital, right? So that's the first thing you gotta notice. So we have to use this chlorine right here. And the second thing is, let's look at the nucleophile. Nucleophile is negatively charged. Okay, so that's a strong nucleophile. Now I gotta look here. The chlorine is secondary, right? Now here I have to decide if it's gonna form an E2 or an SN2. Now we know that this is not a strong base, right? This is just a strong nucleophile. So what's gonna happen is, I'm just gonna draw the mechanism here. You're not supposed to draw the mechanism of this section of the test. So just for the sake of learning, I'm just gonna draw out the mechanism. So what's gonna happen, this negatively charged is gonna attack from the bottom and kick off this chlorine, right? Once the chlorine is kicked off, it's gonna add this SCH3, but remember, this is an SN2 reaction. And if it's an SN2 reaction, you're gonna have a full inversion, right? So now the group that I'm adding is gonna be on a wedge, so SCH2CH3, and then the hydrogen is now on a dash, and that would be the product. Also, the other thing I will mention is the MSO. Just remember, the MSO is a aprotic solvent. Aprotic solvent. Right. Alright, so now moving on is, well, first of all, when you look at this, you'll be like, oh, well, what is this? But let's not worry about this one first. So let's look at the Br here. The Br is a tertiary, right? So it's a tertiary, so usually if we want to think about it this way, it's going to be SN1 in E1 favor, right? But the things you gotta notice is that this base right here is a bulky base. And this is also known as T, triethyl amine. So what's gonna happen is that this nitrogen with the lone pair is gonna come in and grab the adjacent hydrogen. But remember, when we're talking about bulky base, always the major product is going to be the one that is less substituted. The reason to why is that is, let's pretend you have those 2 hydrogens, A and B. Call this hydrogen A and hydrogen B. This is a bulky base. When it comes in to attack, it would rather come in and grab hydrogen B. The reason to why is that is because there's nothing next to it, right? It's more empty space. But once this space comes in to attack and grab this hydrogen A, there are those 2 groups next to it, which can form steric hindrance, and thus will become less stable, and thus will produce the minor product. So once this nitrogen grabs the hydrogen, it's gonna kick off this double bond down and kick off the Br. Alright, and then you're gonna end up with this product with the double bond right here, and then the other product, because she wants you to draw both She wants you to draw both of them, right? Can't speak. Now this lone pair can also grab this hydrogen and kick off the lone pair right here. The lone pair and form the pi bond and kick off the bromine, and then your product for the green one is gonna be right, and then you're gonna have the double bond is gonna be right here. Let us see issue. I am forgetting something this one. Yeah, I drew this one wrong, the purple one. So 1, 2, 3. Let me just adjust the purple one. 1, 2, 3, 4. Yep, I drew this one wrong. So those are my two products. So as I mentioned before, because this is a bulky base, this is a triethylamine, what's gonna happen is the bulky base is gonna wanna grab the hydrogen B, and then you're gonna end up with this as your major product because this one is the less substituted. So you're gonna end up with something like that. And then your minor is gonna be the green one. Which is the more substituted one. So some people like to remember it as like, oh, if there's a bulky base, the less substituted one is the more stable. But I like to think about it as where is the space gonna grab which hydrogen. This hydrogen B is more freely available. There is less steric for the base to come in and grab it because this base is pretty big, so it wants lots of space, right? This is how I like to think about it. Some people think about it as like, make sure when you have a bulky base, the less substituted one is gonna be the more stable one. So, alright, so now coming to number 5, immediately you have a cyclohexane, that's what you see, and then you have different leaving groups. You have this leaving group and you have this leaving group right here. And now the other thing is you can see is you have a strong base, right? By the way, this CH3CH2OH, this is just a solvent, it's just being in the reaction. Now, it's a strong base, so you know it's gonna form either a E1 or an E2, right? Well, it's gonna be an E2 here because it's a strong base, right? So now the hard part of this reaction is being able to determine which chlorine are you gonna use. As I mentioned before, how you wanna recognize which chlorine is. First of all, you want the rule that applies here is gonna be trans diaxial. What that means is you're gonna have your leaving group and your hydrogen both have to be on an axial, right? So knowing that, to form the more stable chair conformation is you want to have your third butyl right here on equatorial, right? So anything that is on a wedge right here, so the hydrogen right here that is on a wedge has to be axial, right? So this chlorine is gonna be, well, the hydrogen that is on a wedge is gonna be equatorial. This chlorine right here has to be axial. Now moving on, this wedge right here has to be axial, and this chlorine has to be equatorial, right? Because you're alternating. So wedge is gonna be equatorial, the next wedge is gonna be axial, and so on and so forth, right? So we cannot choose this chlorine right here because it's on equatorial, and we don't want that, right? That's not good. Now we have to choose this chlorine. So let me redraw it because this is too crowded now. So I have a hydrogen right here, and I have a third butyl right here, CH3, and I'm gonna have a Cl right here, right? And I'm gonna have a hydrogen. Let me not draw the hydrogen right now. I'm gonna have a CH right here, and I'm gonna have a Cl right here. I want to do something a little bit different in this reaction, and I'm gonna put one of those hydrogen is gonna be a deuterium. Deuterium is just an isotope of hydrogen, right? It's the same thing as hydrogen technically. Right, so now if I look at these two, I have a hydrogen right here, and I have on a dash, I have the deuterium. Now, as mentioned before, we mentioned that this hydrogen is going to be on axial, right? And we know that this Cl is going to be on axial. So you gotta be able to know which ones are gonna be on axial. So we know that this deuterium is gonna be on equatorial, this hydrogen is gonna be on axial, and this chlorine is gonna be on axial. So we mentioned that we know that this is gonna be the chlorine that we're gonna be using. But now I gotta decide which one I'm gonna use. Am I gonna use the hydrogen or the deuterium? But look, if I look at the deuterium, it's on the equatorial, so that's not good. So I have to use the hydrogen. So what would happen here is that this CH3O minus is going to come in, grab the hydrogen, kick off the double bond right here, and kick off the leaving group leaves. And then your product would look something like this. Remember, I added the deuterium just to show you why I chose the hydrogen, because the leaving group and the hydrogen, they both have to be on axial, as I mentioned right here. So now, if I draw it out, I'm going to have a double bond. Third butyl right here, CCH3, 3 times with a hydrogen, and then I'm gonna have a CH right here, and then I'm gonna have a chlorine, and then the deuterium is gonna be right here. You see, I didn't touch the deuterium. If your deuterium was on axial, I'm allowed to use deuterium as a hydrogen, right? Because it's just an isotope of hydrogen. So if the deuterium was on an axial, I would have used the deuterium. Right, and that's why I'm just using the deuterium to show you that we have to use the axial hydrogen. All right, so now moving on, we have this is a vinylic dibromination. So this is an E2-like reaction, but instead of having a bromine and a hydrogen, you have two bromine, two adjacent bromines right here. You see that? So what happens here is that this iodine is going to come in, grab a bromine, kick off the electrons, and then kick off the bromine. Right? The reason why iodine was able to grab this bromine is because this bromine is leaving without its electron, right? But here, before we like jump into that, I would like to mention that there's something really wrong. We cannot do that, right? Because this reaction, as I said, is like E2-like reaction. And remember, one of the conditions for you to be able to perform an E2 is that you want to have your leaving group and your hydrogen to be trans to each other. And those are cis. So what you have to do is you have to flip this. So I want to have a Br up here, and this Br stays the same, with a CH3 right here, CH2, CH3. I think that's the same example that she did in class. I'm not sure though. So once I flip this Br right here, how you want to flip it is like it's like a propeller, right? So you hold this one down inside. Once you flip this one up, those two are gonna flip the conformation. So my methyl is now on a dash, and my ethyl is now on a wedge. So that would look something like this. My methyl like this, and my ethyl is going to be on a wedge. And this is really important because we're forming a double bond at the end, and at the end, I'm going to have the dashes on the same side, and the wedges are going to be on the same side. So now, let's just draw the mechanism. What's going to happen is that this iodine is going to come in, grab the bromine, kick off the electrons, and then the Br leaves. And then I'm going to end up with a double bond. I want to have my wedges on the same side. So CH3, CH2, CH3. I'm just going to write ethyl here. And then on the bottom, I'm going to have a CH3 right here. And I'm going to have a ethyl here. And another thing is, it doesn't matter which one's going to go point up and which one's going to point down, right? Just be consistent. So if your dashes are like pointing up, let's pretend here my wedges, because I chose my wedges pointing up. My wedges are pointing up. I'm going to have them pointing up, both of them, right? And then if my dashes are pointing down, they're going to be pointing down. I can also flip it. I can have my dashes pointing up and my wedges pointing down. It does not matter. Just be consistent. Alright, so now moving on to mechanism. This is one of the best part of this test. This is like the most fun. Alright, so usually in this part of the test, especially now as test 2, you most of the time gonna see SN1 E1 just because there is actually a mechanism, right? SN2 is just a one-step process. Remember, this is a secondary bromine, and you have a weak nucleophile. So the first step what's going to happen is this leaving group is just going to leave, and then you're going to end up with a positive charge right here. Now, if you look here, there's something really good that can happen. What can happen is you have a hydrogen right here, and you can do a hydride shift. The only time you do a hydride shift, so only time you do a hydride shift is when you go from a primary to secondary or secondary to tertiary. Unless also she tells you like, oh, do a hydride shift here. Or she gives you a product where it shows you that there is an obvious hydride shift. I don't know if you guys learn about methyl shift, but there's also a methyl shift. Pretty sure you learned about that later on. So to draw the mechanism for the hydride shift is you're gonna point an arrow like that, and that's your hydride shift. 1, 2, 3, and then there's one hole. And now I went from a secondary carbon cation to a tertiary carbon cation. Right? Now, if I look at the products, I can see that I have one SN1 and I have two E1s. Let's see, first of all, let's just do the SN1, the easy part, where I'm just gonna have the CH3OH, the CH3, is it CH3OH? Yeah, CH3OH, with the lone pair on the oxygen, act as a nucleophile and attack the electrophile, the positively charged carbon, and I'm gonna end up with double bond right here, with an OH, CH3, and then there is a positive charge right here. Now to get rid of this positive charge, I need to deprotonate. Now I have two things that I can use to deprotonate, either a Br minus, because remember this Br that left right here is going to form a Br minus, or I can use a CH3OH with the lone pair. So if I would use CH3OH, I would just use the lone pair, grab this hydrogen right here and kick this one off. If I use the Br, then I'll end up using the negative charge, and I take the hydrogen and get rid of this positive charge. Either way, I'm gonna end up with the same product. So that would be 1 and then OCH3. So that's my first product. That's right here. Now we have to focus on the E1 part. So now when you're looking at when you look at the product that she gave you, you notice that actually no, she gave you two options for OCH3 and then one for E1. So there's another SN1 before we jump to E1. So the thing you notice here is that this positive charge is on an allylic carbon. Again, allylic carbon is a carbon adjacent to a double bond. So what happens here is I can have a resonance, and this is why allylic, I should mention that before, but when you have a SN1 allylic reaction, it's much faster than a primary, right? Just to mention that really quick. And the reason to why is that is because you'll have a resonance contributor, which stabilizes the transition state. So now you have a positive charge right here, and now I can use the same thing and use this product to do the same thing. So what's going to happen is a CH3OH, the lone pair is going to come in and attack this thing, and you're going to end up with OHCH3 positively charged. Again, you can use Br minus or CH3OH to get rid of, to deprotonate. So I'm just gonna I like using Br minus just because it's smaller. So Br minus is gonna come in, grab this, and push those electrons back to the oxygen, getting rid of this positive charge. So now Did I count these right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. 1, 2, 3, 4. There's a double bond right here. And then you're gonna end up with the end no CH3. So that's my second product. Yep. That's correct. That's correct. Now looking at my third product, I formed two double bonds. And if you notice something, she formed a double bond at this position, right? This is my initial one, and I have a double bond right here. So I'm gonna redraw this thing. So I'm gonna redraw right here. I like to redraw just for the ease of grading it. Well, you're not gonna write the test, right? It's just gonna be multiple choice. I keep forgetting that. Okay, positive charge right here, and then a double bond. So now the adjacent hydrogen next to this positive charge is gonna be right here. And I'm gonna have this weak base that I formed, the CH3OH. The CH3OH is gonna come in, grab this hydrogen, and form a double bond, and I'm gonna end up with this product. And this is my third product. So yeah, that's pretty much it, right? It's not that hard. Just make sure you keep track of what you're doing, right? And you should be good. Also, here you can also use or Br minus, same thing. You can grab this hydrogen too. I don't know. It doesn't matter which one exactly you choose, but just to keep the option open. Now, moving on to synthesis. This is actually a pretty fun part too. So synthesize a molecule below from alkane of 4 carbons or less and any inorganic reagents. So 4 carbons or less. This is our starting material. So when we're doing those types of synthesis, how I'd like to do is I'd like always to separate my functional groups. So if I need to split the molecule, I'll split it at a point where I have 2 functional groups on 2 separate molecules. But before we start into splitting this thing, we notice that there's a Br on an allylic position, right? So on an allylic position right here. So remember the reaction NBS and light. So I would start, well, this is the end of the reaction, but I would start with using NBS and light. Right? Because remember, when I do NBS and light, I'm gonna form a radical right here, and this radical then will connect to ABr. Just keep that in mind. I'm gonna erase this. So now it's much easier for me to split it. I only have 2 functional groups. So I'm gonna try my best to split it right here. And the reason to why I want to split it right here is because I'm gonna have 1 functional group on this part and then the other functional group right here. So the ether is separate so I have 2 functional groups. I have the ether and I have the alkene. The ether, I want to have it on like the oxygen now. It's gonna be on a different molecule than the alkene. So let's bring it down the middle. To form this to form this molecule, I need an oxygen right here, a double bond, Br. Now, a common mistake that people do is they just use O minus here. You cannot use O minus is because then you are gonna have a what's it called, a E2 reaction, and you don't want that. That's why you have to, as much as Dr. Bean discourages the use of SN1 because it's not as good as SN2, but you cannot do SN2 here. So you have to use OH. And then don't forget, when you're doing OH, you have to use heat just to increase the product because SN1, E1 doesn't give you that much of product to work with. So that's why you add heat to increase the amount of product. Now to form this Br right here, again, it's the same thing, so I can just use NBS and light. It's on an allylic carbon. And then I'm going to solve a double bond. Now, to form this double bond, we only know 1 reaction as of right now, and it is to just use E2, right? And using E2, you can either use terbutoxide or you can also use like CH3O minus, right? in this case, it doesn't matter, but you have to notice sometimes when you have to choose which one to use, right? So I'll try to give an example of that in a second here. So let's just pretend we're going to use terbutoxide. And if you have a terbutoxide, you can just start with a bromine, right? To form this bromine, I can just use Br2 and light. Br2 and light. Now, let me just give an example of a double bond where you have to decide if you have to use terbutoxide or a small base. So let's pretend we have. Let's pretend you want to form this group right here, right? To form this group, you cannot use a bulky base because your initial product you're going to start working with is going to be a Br right here, right? If you use a bulky base, if you were to use a bulky base right here, this bulky base is going to come in, grab this hydrogen, and form the double bond right here. And then you're going to end up with this product. So that's why you have to be careful which base you choose. So in this case, I would choose a small base. So something like a CH3O minus. So if I use CH3O minus with the Br right here, this is going to come in and grab this hydrogen right here and kick off the electron and then kick off the Br, and then you'll get the right product. So you see how you have to be smart about which base you want to use. You always have to use a strong base because it's going to give you the better product and form an E2, but you gotta know which one you have to use, a strong bulky base or a small strong base. So yeah, just keep that in mind. Now to form this OH, I'm just going to do a hydration reaction. So I'm just going to use H2O and heat. And then I can start with a bromine. And then to form this bromine, which I already made, so I don't actually have to draw the reaction, but I'm just going to write it down because it's much easier. So Br2 and light. And then I'm going to end up with this. I forgot something really important here. Something that, the thing that I forgot is the excess. I got distracted. So excess is really important to put. During my time when I took the test, she moved 2 points for everyone who forgot this. Right? The reason why you want to put excess is to avoid polybromination. Right? Just make sure you put the excess there. It's really important. It plays a major role in the reaction. Alright guys, so moving on to the multiple choice that I gathered from the ACS booklet is, so the first question is, what would be the major product of the dihydrohalogenation of 2-chloropentane by KOH? So let's start by drawing out the reactant, which is 2-chloropentane. So 1, 2, 3, 4, and 5, and then you have a chloro on the second carbon. CH3, H, CH2, CH2, and then CH3. And then she's looking for the dihydrohalogenation. So what's gonna happen here is that this KOH is a small strong base. Is gonna come in and grab the hydrogen and then form the double bond, right? But now we gotta decide which hydrogen is gonna grab. Is it gonna grab this hydrogen A or this hydrogen B? Now we know that KOH is a small strong base, right? So we know that it's gonna form the more substituted, or it can grab the more sterically hindered hydrogen. So knowing that, we know that this KOH, which is K plus OH minus ionic bond, can come in, grab this hydrogen B, kick off the electron, and form the pi bond, and then the Cl would just leave, and then we're gonna end up with CH3. CH, double bond, CH, CH2, CH3. And then looking at the multiple choice options that we have, the answer would be, it's going to be B. So that's pretty straightforward. Now, which is the order from the fastest to the slowest for the rates of the SN2 reaction of these alkyl bromide with CH3S minus with DMSO? Remember, DMSO is just a protic solvent. so it doesn't play a major role in the reaction as much as CH3S-, which is our nucleophile. Now remember what I said about SN2, and I would like to add a couple things other than that determines the speed is going to be primary better than secondary, and then that is much better than tertiary. There's two things that can also make it faster than even having it primary, right? And that would be the allylic carbon. The allylic carbon is about 40 times faster. Something that's even faster, oh, by the way, the allylic carbon is, remember, is the carbon adjacent to the double bond. And the reason to why is because this will be resonance stabilized, right? It can resonate. And there's one that is even faster. It's called the benzylic carbon. And that one would be about 100 times faster. And that would look something like this. It's a benzene ring, and there is a bromine adjacent to it. Now, looking at all of these, the first thing that we notice immediately is that this Br is on an allylic position. So immediately 2 has to be our fastest, right? So looking at all of these, the only one that start with the fastest is 2, so B is my answer, right? But let's look at the other 2. This one right here is a secondary, and this one right here is a tertiary, right? It's connected to 3 carbons. So looking at these, we know that 3 is faster than 1, so 2, 3, 1, so that would be my answer. Alright, so looking at number 12, we can see here that they're asking us which carbocation would not likely to undergo rearrangement. So, I remember when I mentioned mechanism that rearrangement happens only if you're going from like a secondary to a tertiary or a primary to a secondary. Something that's more stable, right? You never want to go from like a tertiary to a secondary. Right? That never happens. Now, I don't know if you guys study about methyl shift. I know you guys study for a hydride shift, so it might get a little bit more complicated. So which compound would not be likely to undergo rearrangement? So this one right here, this hydrogen can come here, and then you're gonna have a CH, the positive charge on the tertiary. So it goes from a secondary right here. So this hydrogen will go there, and then it's gonna end up with a CH3, CH2, a C, CH3, CH3 positively charged. So now it's tertiary. So that's a good thing. Now, let me skip B for now, and then we'll come back to it. Let's look at C. This is a tertiary. Well, if I do a hydride shift right here, I'm going to go to a secondary. If I do a hydride shift from this side, I'm going to go to a primary. So that's not possible at all. Let me just draw the outcome to what you get if you do a hydride shift from both sides. CH2, C, CH3, positively charged, CH2, CH3. Now this is a primary, and the other outcome would be a CH3, CH, a CH3, CH, and then a CH3, and then a positive charge. So that would be a secondary. So you were going from a tertiary to a primary, or tertiary to a secondary. So that's not good at all. So that would be the answer. But let's keep going. Now the other one would be this one. If you have a CH3, a CH, CH2 positively charged with a CH3. Now what would happen here is this hydrogen is going to move here. Oh, my bad. I meant this hydrogen will move to this side, and then you're going to end up with a CH3, a CH2, not CH2, a C, CH2, and the positive charge would be here. So you went from a primary to a tertiary. So you went to a more stable thing, so that's good. Now let's look at B. I'm going to write this in there red, so, because this one is kind of, I don't know if you guys covered this, so I gotta go in depth about it. CH, C, CH3, CH3, and then you have another CH3, I think. Yep, that's correct. And then you have positive charge right here. So now if you look here, you can move this hydrogen from this side, but then you're gonna end up with a CH2, a CH2, a C, CH3, CH3, and CH3. You're gonna end up with a positive charge right here. So you went from a secondary to to a primary. So that's not good. You don't want that to happen. Now, the other thing that you can do is you can do a methyl shift. So you take the CH3 right here, move it to this side, and then you're going to end up with a CH3, a CH3, a carbon, CH3, CH3. So that would be a tertiary carbon cation compared to a secondary carbon cation. So that's actually possible, and that's why B is a possible rearrangement. So that would only get us to C as the wrong answer, because you cannot go from a tertiary to a primary or a tertiary to a secondary. Now looking at number 20 here, which of the mechanism steps shown is not a reasonable one in the mechanism to describe the formation of a 2-methyl-1-butene by dehydration of 3-methyl-2-butanol? So let's look at the mechanism of how the dehydration occurs. So 3-methyl-2-butanol. So butanol is 4 carbons, 1, 2, 3, 1, 2, 3, and 4, and then there's no H on the second one. You're not supposed to know the name of this one. Actually, they give it to us. I didn't see it. So CH3, C, there's CH3 right here, and there's a hydrogen, and CH3. So I'm gonna use, for the dehydration of this reaction, I'm gonna just use SO4, H2SO4, HOSO3H. When you're doing a dehydration mechanism, you always want to draw it this way so you can show the arrow pushing of this hydrogen right here. You always want to draw the H2SO4 like that. Oh, sure. So the first step to what happens is this oxygen is going to grab the hydrogen, and then you're going to end up with a CH3, CH3, COH2, positively charged. So now this OH2, H2O is going to be positively charged, which means it's a good leaving group now. Alright, now the next step to what happens is that this H2O is just going to leave. Oh, this hydrogen is around there. And then we're going to end up with a CH3, CH3, CH, positively charged, and then the CH3. Now, the last step that was going to happen is, what we lost here, a hydrogen. Now the H2SO4 became a SO3H, or OSO3H minus. Now that's going to act as a base, and it's going to come here and grab this hydrogen and kick off the double bond, and then the result would be a CH3, CH3, double bond, CH, CH3. So that would be our result. So she's asking which one of these is going to be the least likely to be the mechanism. So to be one of the steps of the mechanism. So we know that this happened in our mechanism, right, where the H2O leaves. This happened right here. Now let's look at B. There's a hydra shift that occur right here. Hydra shift? Yeah, she made a hydra shift, which is also possible, right? This is a possible mechanism that I didn't draw, but you could also have a hydra shift. So I should have mentioned that here. So you can also have the other option here is you can have a hydra shift because you're going from a secondary to a tertiary, which is also a possible outcome, right? CH3, CH3, CH2, CH3, and then I have positive charge right here. So that's also a possible outcome. So here we're good still. And now if we look at C, it went from a primary, it went from a secondary to a primary here. That's not possible at all, right? This is not a possible outcome. Now the other one is where they use the lone pair on the oxygen and you grab the hydrogen, and this is the same thing as my last step. I just used a different reagent. I used H2SO4, they used H2O. So that's also possible. They used actually H3O plus. I used H2SO4, which are both acids, and you can use them in dehydration. So the wrong answer in this case is going to be C. Well, the wrong choice of mechanism is not a reasonable outcome, because you went from a secondary to a primary. Now moving on to 31. Which is the proper representation of the flow of electron in the E2 elimination? So remember, in E2 elimination, what happens is, let's try this. Let's just do the mechanism really quick here before. COTAS, and then the CH. Just remember, OTAS is just a good leaving group, right? And then you're adding C2H5 O minus. Strong base with a secondary good leaving group. So what's going to happen here, it's an E2 mechanism with the hydrogen here. This negative charge is going to come here, grab that. This is going to kick off, and then it's going to get rid of this OTAS group. So I'm going to end up with a CH3, CH, a double bond, CH, and then CH3. So yeah. So now looking at this, let's look which is the proper representation of the flow of electrons in the E2 elimination. So they grab the negative, so this is correct. This is one of the options, so let's keep going. This is super wrong, right? Because you never want, like, how's the hydrogen that's like partially positively charged going to grab the negative? That's not possible at all, right? Yeah, this is just wrong. That doesn't happen. Now the second thing is this O minus attacks here and form an OCH3, and then, yeah, I don't know what they're trying to do here, but I would assume that the result will look something like this. So they're like combining a SN2 with an E2 here, or something like that. Yeah, this is not even possible, right? Like, you either want to add or eliminate. You cannot add and eliminate at the same time. Now the last thing is the leaving group leaves, and then you end up with a positive charge and the O negative attacks. Remember, this is an E1 mechanism. Remember, E1, the leaving group leaves. It's a two-step process. And that's not the mechanism of E2, so the right answer would be A. Alright, so that's what I have for today. Good luck, guys, on your test, and I hope you do the best you can.